Hello there and welcome back to the Science Sleepy Minds. You're lying in bed right now, perhaps scrolling through your phone, perhaps already half convinced that sleep is just around the corner. But here's something that might keep your neurons firing for just a moment longer. The floor beneath your bed is experiencing time differently than your pillow. Not metaphorically, not poetically, literally. The atoms in your floorboards are aging at a measurably different rate than the atoms in the soft cushion cradling your head. The difference is tiny, billionths of a second over your entire lifetime, but it's real, it's measurable. It's one of the strangest facts about the universe you inhabit, and you probably won't survive this video without questioning everything you thought you knew about reality itself. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Drop a comment telling me where you're watching from and what time it is there. Are you in Tokyo at 3 in the morning, São Paulo at midnight, a small town in Nebraska where the crickets are louder than your thoughts? I love knowing that these words travel across time zones, reaching people in darkness all around this spinning rock. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The fabric beneath you, your mattress, your sheets, the very space you occupy, is stranger than any fantasy novel could conjure. You exist within something called spacetime, a four-dimensional structure that Albert Einstein described over a century ago, and here's the uncomfortable truth. We still don't fully understand it. We use it. We measure it. We've built technologies that depend on it, but comprehend it. Truly wrap our limited primate brains around what it actually means. That remains stubbornly out of reach. You breathe in slowly, the air fills your lungs, and during that single breath, you've travelled about 30 kilometres through space as Earth spins on its axis. You've also hurtled roughly 500 kilometres along Earth's orbit around the Sun, and if we factor in the solar system's movement through the Milky Way galaxy, you've covered something like 3,000 kilometres, all while lying perfectly still. The universe is moving you whether you consent or not. This is where tonight's story begins, with the realization that stillness is an illusion. Movement is relative, time is flexible, space is curved, and the comfortable separation you maintain between here and now is far more complicated than your everyday experience suggests. For most of human history, nobody questioned time. It flowed, it passed, it marched forward with the reliability of a German train schedule. Though honestly, German trains aren't as punctual as their reputation suggests. Historians still argue whether that stereotype emerged from wartime propaganda or genuine 19th century efficiency. But the point remains, time seemed absolute, universal, the same everywhere and for everyone. If you lived in ancient Egypt building pyramids under the scorching sun, time passed for you at exactly the same rate it passed for a hunter-gatherer in prehistoric Britain or a philosopher in classical Greece. This seemed so obvious that nobody bothered questioning it. The sun rose, the sun set, seasons cycled, people aged. Time was time was time. This assumption burrowed so deeply into human consciousness that even the greatest minds took it for granted. When Isaac Newton formalized the laws of motion and gravity in the late 17th century, he built everything on this foundation. Time in Newton's universe was like a cosmic metronome clicking away in the background, utterly indifferent to whatever was happening in the physical world. Space, meanwhile, served as an empty stage where objects performed their mechanical dance. Newton himself acknowledged that he didn't truly understand gravity. His equations described it beautifully. They could predict planetary motions, explain tides, describe the arc of a cannonball with breathtaking accuracy, but they didn't explain what gravity actually was. How did the sun reach across 93 million miles of empty space to pull on Earth? Through what medium did this mysterious force propagate? Newton famously wrote that he framed no hypotheses about gravity's underlying nature. He gave us the math. The meaning remained elusive, and so the clockwork universe hummed along. For over 200 years, physicists refined Newton's framework, extending it to explain electricity, magnetism, thermodynamics, and the behavior of gases. The 19th century belonged to confident scientists who believed they were merely filling in details on a nearly complete picture. A few minor puzzles remained, some odd experimental results with light, some quirky behavior of Mercury's orbit around the Sun. But surely those would yield to clever mathematics soon enough. Lord Kelvin, one of the era's most celebrated physicists, allegedly remarked around 1900 that physics was essentially complete, with only two small clouds on the horizon. Those clouds were the strange results of experiments measuring the speed of light and the unexpected radiation patterns from hot objects. Minor issues, surely. What nobody anticipated was that those two small clouds would unleash hurricanes that would demolish the entire Newtonian edifice. The first hurricane was quantum mechanics, which shattered any hope of a purely deterministic universe. The second was relativity, which revealed that Newton's absolute time and absolute space were fantasies, useful approximations for slow-moving everyday objects, but fundamentally wrong about the nature of reality. You settle deeper into your pillow, feeling the weight of your body against the mattress. Every atom in your flesh is participating in Spacetime's strange geometry right now. The electrons orbiting in your cells, the quarks huddled inside your protons, the mysterious fields that give particles their mass, all of them exist within this fabric that Einstein spent his life trying to understand. Here's a quirky historical tidbit that rarely makes it into physics textbooks. Einstein nearly abandoned physics entirely before his revolutionary year of 1905. His academic career had stalled. No university would hire him. He worked as a third-class patent examiner in Bern, Switzerland, evaluating applications for inventions, many of them involving electrical timing systems used to synchronize clocks across railway networks. Some scholars suggest that this daily exposure to practical problems of timekeeping and simultaneity planted seeds that would later bloom into special relativity. The mundane bureaucratic job that seemed like a dead end may have been exactly what his mind needed. The universe, it turns out, has a sense of humour about destiny. The world you inherited came wrapped in certainties that felt unshakable. Time flowed forward, space spread outward. The two had nothing to do with each other beyond providing a backdrop for things to happen. This was Newton's gift to humanity, a cosmic framework so intuitive, so aligned with everyday experience, that questioning it seemed almost absurd. You can sympathise with physicists of the 19th century. When you drop a ball, it falls. When you throw a ball, it arcs through the air and lands predictably. When you synchronise your watch with a friend's before parting ways, you trust that both watches will show the same time when you reunite, assuming neither is broken. These experiences reinforced Newton's vision constantly. The universe behaved like a vast machine, gears turning in perfect synchronization, and time served as the universal lubricant keeping everything running smoothly. Newton himself was careful about his claims, more careful than many who followed him. In his monumental work Principia Mathematica, published in 1687, he distinguished between absolute time and the relative time we actually measure with clocks. Absolute time, he proposed, flowed uniformly regardless of anything external. It was mathematical, true, pure. The time we experience and measure was merely an approximation of this perfect background flow, an approximation that worked extraordinarily well, but an approximation nonetheless. This framework proved so successful that generations of scientists saw no reason to question it. Astronomers predicted eclipses centuries in advance. Engineers built bridges that didn't collapse. Artillery officers calculated trajectories that landed shells on target. Every practical application reinforced the Newtonian worldview. When your equations work this well, why look deeper? But cracks were forming, hairline fractures that most scientists dismissed or simply didn't notice. The first major fissure appeared in the study of light. You see, physicists in the 19th century understood light as a wave, similar to sound waves travelling through air or ripples spreading across water. Waves, they reasoned, needed a medium to travel through. Sound couldn't propagate in a vacuum. No air meant no vibrations, meant no sound. So what medium carried light waves? They called it the luminiferous ether, this hypothetical substance filling all of space. It had to be incredibly stiff to transmit light's high-frequency vibrations, yet somehow permit planets to pass through it without resistance. A peculiar substance indeed, rigid yet intangible, everywhere yet undetectable. Physicists simply trusted that cleverer experiments would eventually reveal its properties. In 1887, Albert Michelson and Edward Morley conducted what they hoped would be a definitive test. Their reasoning was elegant. Earth orbits the Sun at roughly 30 kilometers per second. If we're ploughing through a stationary ether at that speed, then light should travel slightly faster when moving with Earth's motion, and slightly slower when moving against it. Just as swimming downstream feels easier than swimming upstream, their precision interferometer would detect this difference. It didn't. No matter how they oriented their apparatus, no matter what time of year they measured, the speed of light remained stubbornly constant. The ether wind simply wasn't there. This result was so unexpected, so contrary to everything physicists believed, that most simply assumed something was wrong with the experiment. Maybe the ether was being dragged along by Earth. Maybe the apparatus contracted slightly in the direction of motion in just the right way to hide the effect. Clever explanations proliferated, each more convoluted than the last. Historians still argue whether Michelson and Morley themselves fully appreciated the revolutionary implications of their null result, or whether they viewed it primarily as a technical puzzle awaiting resolution. Meanwhile, another crack was widening. Maxwell's equations, which beautifully unified electricity and magnetism, contained a peculiar feature. They predicted electromagnetic waves, light being one example, would travel at a specific speed determined only by fundamental constants of nature. This speed wasn't relative to anything. It wasn't measured from any particular reference frame. It simply was, floating in the equations like an unexplained universal constant. This troubled physicists who thought carefully about it. Speed relative to what? In Newton's universe, speed was always relative. A train moving at 60 kilometers per hour meant 60 relative to the ground. If you walked down the train's aisle at 5 kilometers per hour, you moved at 65 relative to the ground, but only 5 relative to the train. Speed depended on your reference frame. Yet Maxwell's equations seem to claim that light travelled at 300,000 kilometers per second, period, without specifying 300,000 relative to what. Here's where a young patent clerk enters our story. Albert Einstein, born in 1879 in the German city of Ulm, had been fascinated by these questions since adolescence. At 16, he tried to imagine what it would be like to chase a beam of light. If you travelled alongside light at light speed, would the light wave appear frozen? Would you see electric and magnetic fields suspended motionless in space like a stopped movie frame? Maxwell's equations said no. They contained no provision for stationary light. Light at rest wasn't a valid solution. This bothered young Einstein deeply. The equation seemed to be telling him that light would always zip away at the same speed, no matter how fast you pursued it. But that contradicted everything Newton's mechanics had established about relative motion. For nearly a decade, this puzzle simmered in Einstein's mind. He attended university in Zurich, graduated without distinction, failed to secure an academic position, and eventually settled into his patent office job in Bern. Far from major research institutions, lacking access to advanced laboratories, working regular bureaucratic hours, he seemed an unlikely candidate to revolutionize physics. But sometimes the universe places people exactly where they need to be. The patent office gave Einstein steady income and, crucially, thinking time. His job wasn't intellectually exhausting, quite the opposite. Evaluating patents for electrical devices, including various clock synchronization systems, he engaged daily with practical questions about how signals traveled and how different locations coordinated their timekeeping. These mundane problems may have kept the puzzle of simultaneity fresh in his mind. His colleagues included a few friends who shared his intellectual interests. They formed an informal discussion group they mockingly called the Olympia Academy, debating philosophy, physics, and literature over meals and walks. These conversations sharpened Einstein's thinking, encouraged his rebellious questioning of fundamental assumptions, and provided intellectual companionship during otherwise isolating years. You shift slightly in bed, perhaps adjusting your blanket. Einstein's story feels almost mythological now, the lone genius scribbling equations in obscurity before stunning the world with his brilliance. But it wasn't magic. It was years of sustained, frustrating thought about problems everyone else either ignored or addressed with increasingly baroque workarounds. Einstein's genius lay partly in his willingness to take the experimental evidence at face value, to accept that the Michelson-Morley result might be telling a deeper truth rather than hiding an experimental error. Young Einstein possessed something rarer than mathematical talent, the audacity to question assumptions so basic that nobody recognized them as assumptions at all. You and I take for granted that simultaneous events are simultaneous for everyone. If two firecrackers explode at the same moment in different places, observers might hear them at different times. Sound travels slowly after all, but we assume the explosions themselves happened objectively simultaneously. Einstein asked a dangerous question. How do we actually know? Consider his most famous thought experiment. You're standing on a railway platform as a train rushes past. Lightning strikes both ends of the train at the same instant. Or so it seems to you. Standing exactly midway between the strike points, you see both flashes reach your eyes simultaneously. Fair enough. But what about a passenger sitting in the middle of the train? By the time the light from both strikes reaches her, the train has moved forward slightly. Light from the front strike has to catch up to her receding position. Light from the rear strike finds her approaching. She sees the front flash first. From her perspective, the lightning struck the front of the train before striking the rear. Who's correct? Your instinct screams that simultaneity is absolute. Surely the strikes either happened at the same time or they didn't. But here's Einstein's revolutionary insight. Both observers are equally valid. There's no privileged reference frame from which to judge. Simultaneity itself is relative to motion. This sounds like philosophical wordplay until you realize its implications. If two events aren't objectively simultaneous, then time itself cannot be absolute. Different observers moving relative to each other will disagree about the temporal order of events, and neither is wrong. Time bends around motion like a river flowing around stones. Einstein didn't arrive at this conclusion impulsively. His notebooks and letters reveal years of circling the problem, trying different approaches, hitting dead ends. He later recalled a moment of clarity that came after an intense discussion with his friend Michel Bessot, a fellow patent office worker. Something clicked. The key was abandoning the ether entirely and taking the constancy of light speed as a fundamental principle rather than something requiring explanation. If light always travels at the same speed regardless of how you're moving, then space and time must adjust to make this true. There's no other way to reconcile the measurements. When you accelerate toward a beam of light, The light doesn't slow down to meet you. Instead, your experience of time and space warps in precisely the way necessary to keep light speed unchanged. In June 1905, Einstein submitted a paper to the prestigious Annalen Physik with a deliberately bland title on the electrodynamics of moving bodies. This document contained no complex mathematics. A high school student could follow most derivations. Its revolutionary power came entirely from rethinking assumptions. Einstein didn't discover new phenomena. He reinterpreted what everyone already knew. The paper begins with Einstein noting a puzzling asymmetry in how physicists described electromagnetic induction. When you move a magnet toward a coil of wire, electric current flows. When you move the coil toward a stationary magnet, current flows identically. The physics seems the same, but the explanations given were different depending on which object was really moving. This bothered Einstein's sense of elegance. Nature shouldn't care about such arbitrary distinctions. He proposed two postulates, two simple statements that everything else followed from. First, the laws of physics are the same in all inertial reference frames. An inertial frame is one moving at constant velocity, not accelerating. This meant no experiment could distinguish between being truly at rest and moving uniformly, because there's no such thing as truly at rest. Second, the speed of light in vacuum is the same for all inertial observers, regardless of the motion of the light source. That second postulate sounds innocent, but it detonates Newtonian mechanics completely. If you shine a flashlight while running, Newton says the light should travel at light speed plus your running speed. Einstein says no, the light travels at light speed period. Your running contributes nothing. This seems impossible until you realize that your measurements of space and time must change to compensate. Here's a quirky tidbit that illustrates how slowly revolutionary ideas penetrate even brilliant minds. Einstein's paper initially attracted little attention. No immediate prizes, no instant fame. Even physicists who read it often dismissed it as interesting mathematics without physical significance. Max Planck, one of the few who immediately recognized its importance, championed the paper and helped establish Einstein's reputation, but this took years, not weeks. Historians still argue whether Einstein actually knew about the Michelson-Morley experiment when developing his theory. His paper doesn't mention it directly. In later interviews, Einstein gave conflicting accounts, sometimes claiming he knew of it, sometimes suggesting it wasn't central to his thinking. Perhaps his memory shifted over decades. Perhaps the question itself reveals our bias toward viewing scientific progress as responses to specific experiments, rather than deep conceptual rethinking. What matters is what special relativity, as the theory came to be called, predicts. And its predictions are bizarre. Moving clocks run slow. Moving rulers shrink in their direction of motion. Mass increases as objects accelerate. Events that one observer sees as simultaneous, another sees as sequential. And beneath all this strangeness lies a counterintuitive truth. These effects aren't illusions or measurement artifacts. They're how reality actually works. You might protest that you've never noticed any of this. When your friend jogs past you, they don't appear compressed or age slower. True enough. These effects are utterly negligible at everyday speeds. They become noticeable only as you approach light speed, which nothing with mass has ever achieved. At walking speeds, the time dilation factor differs from 1 by about 1 part in 10 quadrillion. At jet airplane speeds, it's still only 1 part in 10 trillion. The universe hides its true nature behind the comforting slowness of human experience. But just because effects are small doesn't mean they're absent. And in the century since Einstein's paper, we've developed technologies precise enough to detect them. The theory's predictions aren't philosophical speculation. They're engineering constraints that modern systems must account for. You carry Einstein's legacy in your pocket every time you check your GPS location. The sleepy world you're dissolving into tonight is one that Einstein reimagined. The darkness surrounding you isn't filled with luminiferous ether. It's just space, interwoven with time, bending and stretching according to rules that your brain isn't evolutionarily equipped to intuit. Rest in that strangeness. Let it become almost comfortable, like a familiar blanket that happens to be woven from impossible geometry. The year 1905 deserves special reverence in the history of physics. You might call it Einstein's miracle year, and physicists literally do, borrowing the Latin annus mirabilis traditionally reserved for Newton's plague year breakthroughs of 1666. Between March and September, Einstein published 4 papers that would each have secured his legacy alone. Together, they transformed physics utterly. One paper explained the photoelectric effect by proposing that light came in discrete packets called quanta, the foundational insight of quantum mechanics. Another provided theoretical confirmation that atoms actually existed by analysing how pollen grains jittered in water. A third derived his famous E equals mc squared equation. And there was the relativity paper, quietly overturning centuries of assumptions about space and time. All this from a 26-year-old patent clerk without university affiliation. You couldn't script a more improbable origin story. Tonight, you're soaking in the consequences of that June paper. Let's trace what happens when you take Einstein's 2 postulates seriously. You accept that light always travels at exactly 299,792,458 meters per second in vacuum, not approximately, not usually, but exactly and always, regardless of how the source or observer moves. What follows? Imagine you're on a spaceship travelling at 90% of light speed past Earth. Your friend remains on Earth, watching you zoom by. You decide to turn on a flashlight pointed in your direction of travel. Common sense suggests the light should leave your flashlight at 90% of light speed relative to you, making it travel at 180% of light speed relative to Earth. Physics should allow simple addition of velocities, but physics doesn't care about common sense. Your friend on Earth measures that flashlight beam travelling at exactly light speed. You measure it travelling at exactly light speed. The beam doesn't know or care how fast you're moving. It simply travels at c, the cosmic speed limit, in both reference frames. For this to work mathematically, something has to give. That something turns out to be time and space themselves. From your friend's perspective on Earth, your spaceship's clocks are running slow. Everything aboard your ship, heartbeats, chemical reactions, thought processes, atomic vibrations, tick slower than their Earth equivalents. This isn't a malfunction. This isn't an illusion. Time genuinely passes more slowly for you because you're moving so fast. How much slower? Einstein derived the exact formula. At 90% of light speed, time aboard your ship passes at roughly 44% of Earth's rate. For every hour that passes on Earth, only about 26 minutes tick by for you. At 99% of light speed, the dilation becomes more extreme. You'd experience only about 7 minutes for every hour that passes on Earth. At 99.9%, the ratio drops to about 2 minutes per Earth hour. The formula involves a quantity physicists call gamma, the Lorentz factor, which depends on velocity. As you approach light speed, gamma increases toward infinity. Time dilation becomes infinite too, which is why nothing with mass can actually reach light speed. It would require infinite energy and would experience time stopping completely. This isn't science fiction. This is measured reality. In particle accelerators around the world, subatomic particles called muons are routinely accelerated to 99.94% of light speed. Muons are unstable. They decay radioactively with a half-life of about 2.2 microseconds when at rest. At those accelerator speeds, they should travel only about 660 meters before half of them decay. Instead, they travel roughly 15 kilometers. Why? Because from the muon's perspective, time slows down so dramatically that 2.2 microseconds of muon time corresponds to much longer laboratory time. The muons literally experience less time between creation and decay because they're moving so fast. Here's a historical quirk that deserves mention. The mathematical framework for these transformations existed before Einstein. Dutch physicist Hendrik Lorentz and Irish physicist George Fitzgerald had independently proposed that moving objects contract in their direction of motion, what we now call Lorentz-Fitzgerald contraction. They viewed this as a physical compression caused by motion through the ether, a mechanical effect that happened to objects. Einstein reinterpreted these same equations completely. There was no ether. There was no physical compression. Space and time themselves behaved differently for moving observers. Same math, radically different meaning. Historians still argue whether Einstein deserves sole credit for special relativity, or whether Lorentz and Henri Poincaré, another physicist who came tantalizingly close to the theory, should share the recognition. Priority disputes in science are notoriously messy. What seems clear is that Einstein alone grasped the full conceptual revolution, while others clung to the mechanical ether explanations that his theory made unnecessary. The implications cascade further. If time dilates, and if space and time are connected, then space must transform too. This manifests as length contraction. From your Earth friend's perspective, your 90% light speed spaceship appears compressed in its direction of travel. If it measured 100 meters long at rest, it appears only about 44 meters long while zooming past. Not because it's being physically squeezed, because space itself behaves differently for moving objects. Again, this isn't illusion. If your friend could somehow measure your ship's length as you flew past, they'd genuinely find it shorter. You, aboard the ship, would notice nothing unusual. Your ruler also contracted by the same factor, so when you measure your ship, it's still 100 meters. Meanwhile, you look at Earth rushing past you and observe that Earth has become slightly compressed in the direction of motion. Everything is relative. Nobody's wrong. This relativity of length has a delightful consequence. Remember those muons travelling 15 kilometers despite their short lifetimes? From the muon's perspective, time passes normally, but from the muon's perspective, the laboratory is rushing past at tremendous speed, and the laboratory's length is dramatically contracted. The 15-kilometer path shrinks to roughly 660 meters in the muon's reference frame, exactly the distance a muon should travel in 2.2 microseconds at that speed. Same physics, different perspectives, consistent results. You're settling deeper into your mattress now, perhaps feeling the pleasant weight of drowsiness. The numbers blur together. That's fine. What matters isn't memorizing formulas, but absorbing the fundamental strangeness. Your everyday experience of time and space is provincial, limited, parochial. The universe operates on grander principles that reveal themselves only when things move fast enough to matter. The equations Einstein scribbled in his patent office apartment weren't meant to stay theoretical. They made concrete predictions, claims about reality that could be tested and potentially falsified. A beautiful theory that fails experimental scrutiny isn't beautiful, it's wrong. Special relativity has survived over a century of increasingly precise tests, each one confirming that the universe really does behave this strangely. You've already encountered the muons. Let's go larger, to machines built specifically to smash particles together at nearly light speed. The Large Hadron Collider, that 27-kilometer ring beneath the Swiss-French border, accelerates protons to 99.9999991% of light speed. At these velocities, time dilation factors reach about 7,500. Each circulating proton experiences 1 second, while roughly 2 hours pass for technicians monitoring the experiment. These aren't theoretical calculations, but engineering requirements. The collider's magnets, radio frequency cavities, and collision timing systems all must account for relativistic effects, or they simply wouldn't work. Particle physics offers another elegant confirmation. When protons collide at such energies, they produce showers of exotic particles. Many of these particles are unstable and decay almost instantly. Their decay rates serve as exquisitely precise clocks. Every single experiment confirms that these moving clocks tick slowly, exactly as Einstein's equations predict. After thousands of experiments across decades, no deviation has ever been found. But perhaps the most relatable confirmation comes from something you might use tomorrow: GPS navigation. The Global Positioning System consists of satellites orbiting about 20,000 kilometers above Earth's surface, traveling at roughly 14,000 kilometers per hour relative to the ground. That's slow compared to light, only about 0.001% of c. But GPS demands extraordinary precision. Your phone determines its location by comparing signals from multiple satellites, measuring the tiny differences in arrival times. These timing differences correspond to position differences, and errors of even a few nanoseconds would translate to errors of meters in position. At satellite speeds, special relativistic time dilation causes satellite clocks to run slow by about 7 microseconds per day. That might sound trivial, but 7 microseconds of timing error translates to roughly 2 kilometers of position error per day. Without correction, your GPS would be useless within hours. There's a twist though, one that points toward deeper physics we'll explore later. GPS satellites also experience general relativistic effects. Being higher in Earth's gravitational field, they experience time differently for reasons Einstein would only fully articulate a decade after special relativity. This effect causes satellite clocks to run fast by about 45 microseconds per day. The two effects partially cancel but don't eliminate each other. Engineers must apply both corrections, which they do automatically to keep GPS accurate. Every time you navigate to a restaurant or track your jogging route, you're benefiting from relativistic corrections. Einstein's theories aren't abstract philosophy, they're baked into infrastructure you depend on daily. Here's an amusing historical note. When GPS was being developed in the 1970s, some engineers doubted whether relativistic corrections were really necessary. The effects seemed too small, too theoretical, too much like physics professor concerns rather than practical engineering. The system was initially built with the capability to apply or not apply corrections, allowing real-world testing. The corrections proved absolutely essential. Nature doesn't care whether engineers believe in relativity. Even more precise tests have been conducted using atomic clocks on aircraft. In 1971, physicists Joseph Haefele and Richard Keating flew cesium atomic clocks around the world on commercial airliners, eastward and westward, then compared them to reference clocks on the ground. The eastward flying clocks lost about 59 nanoseconds relative to ground clocks. The westward flying clocks gained about 273 nanoseconds. These numbers matched predictions from special and general relativity within experimental error. The asymmetry between eastward and westward flights isn't mysterious once you remember that Earth itself rotates. Eastward flights move with Earth's rotation, effectively travelling faster relative to the non-rotating reference frame. Westward flights move against rotation, effectively travelling slower. Different speeds mean different time dilation. The experiment beautifully confirmed that time really does depend on motion, and that the effects are measurable with sufficiently precise clocks. Modern experiments achieve even greater precision. In 2010, researchers at the National Institute of Standards and Technology measured time dilation between two atomic clocks separated by only 33 centimeters of height difference. The higher clock, experiencing slightly less gravity, ran faster by about 90 billionths of a second per 79-year lifetime. This isn't special relativity, it's general relativity, foreshadowing what Einstein would develop later, but it demonstrates how real these effects are. Your head genuinely ages faster than your feet, not by much, but genuinely. These tests weren't conducted to prove Einstein right anymore. That battle ended decades ago. They're conducted to search for tiny violations, hints that relativity might be only an approximation to something deeper. So far, nothing. The theory holds to every decimal place we can measure. You might find this constancy unsettling or comforting, depending on your temperament. The universe follows rules. Those rules are strange, but they're consistent. They don't change depending on who's measuring or where the experiment occurs. There's a stability in that, a kind of cosmic fairness. The laws of physics don't play favourites. As your breathing slows and your thoughts begin to drift, consider the humility embedded in this story. For centuries, humanity assumed time was obvious, intuitive, universal. We built civilizations, scheduled harvests, recorded histories, all treating time as self-evident. Then one clerk with wild hair asked uncomfortable questions, and everything changed. Not because he was smarter than everyone else, but because he was willing to take seriously the possibility that our intuitions were simply wrong. Historians still argue whether Einstein would have developed relativity without the specific technological context of his era. The synchronized railway clocks, the telegraph systems coordinating distant cities, the industrial need for precise timekeeping. Perhaps these practical challenges primed minds to think about simultaneity in new ways. Perhaps Einstein was simply a genius who would have found the truth regardless. We'll never know for certain. What we know is that the universe revealed its secrets to someone willing to listen to what experiments were actually saying, rather than what tradition expected them to say. The twin paradox sounds like a riddle designed to trip you up at parties, which honestly it kind of is. But beneath the cocktail party cleverness lies a genuine insight into how space-time operates, and wrestling with the paradox helps you understand what special relativity actually claims. Here's the setup. You have two twins, identical in every way that matters for physics. One twin stays on Earth, the other boards a spaceship, accelerates to a significant fraction of light speed, travels to a distant star, turns around, and returns home. When the travelling twin arrives back, they discover something disturbing. Their earthbound sibling has aged decades while they've aged only years. Same initial ages, same biological processes, yet time passed differently for each. This isn't a paradox in the sense of logical contradiction. It's a paradox in the older sense, a statement that seems absurd but is actually true. The twins genuinely age differently. If the travelling twin left at age 20 and returned after experiencing 10 years of ship time, they might find their sibling now 60, 70, or even older, depending on travel speed and distance. Their sibling's children would be older than them. Their sibling might be dead. Time dilation has consequences. You might object, wait, isn't everything relative? From the travelling twin's perspective, isn't Earth moving away and returning? Shouldn't the travelling twin see Earth's clocks running slow, leading to the opposite conclusion? That the Earth twin should be younger? This objection reveals exactly why the situation isn't symmetric. The travelling twin accelerates. They feel the engines fire when leaving Earth. They feel deceleration and reversal at the distant star. They feel braking thrust when returning. These accelerations break the symmetry. The travelling twin's reference frame isn't inertial. it changes. The Earth twin's reference frame remains inertial throughout, ignoring Earth's gentle orbital motions, which are negligible for this thought experiment. Acceleration makes all the difference. Special relativity handles only inertial reference frames, those moving at constant velocity. To properly analyze the twin paradox, you need either careful bookkeeping across multiple inertial frames or the full machinery of general relativity, which extends the theory to accelerating observers. Either way, the conclusion stands: the travelling twin ages less. This is calculated, predicted, and would be measured if we could ever conduct the experiment at meaningful speeds. Here's a historical tidbit that grounds this abstraction in humanity's actual spacefaring ambitions. When NASA plans long-duration missions, relativistic effects genuinely appear in calculations. They're utterly negligible for moon missions or Mars expeditions. The speeds are far too slow. But engineers have occasionally computed what interstellar travel would involve. At 1% of light speed, a journey to Alpha Centauri, the nearest star system about 4 light-years away, would take roughly 400 years from Earth's perspective. The travellers would experience almost the same. Time dilation at 1% of c is barely noticeable. But at 90% of light speed, the journey would take about 4.5 years Earth time, while the travellers would experience only about 2 years. At 99%, Earth would wait about 4 years, while the travellers experience roughly 7 months. No technology remotely capable of such speeds exists, of course. Current spacecraft travel at roughly 0.01% of light speed at best, but the calculations illustrate the principle. If you could travel fast enough, you could visit distant stars and return to find your civilization unrecognizably changed. You would be a time traveler of sorts, not into the past, but leaping forward through others' futures while barely aging yourself. Science fiction adores this scenario. Novels and films have explored astronauts returning to find Earth transformed, their families long dead, their nations dissolved. The emotional weight of such stories comes from the hard physics beneath them. This isn't fantasy. This is what the equations say. The universe permits one-way trips into the far future for anyone willing to move fast enough. Historians still argue whether Einstein himself fully appreciated the twin paradox's implications when he first developed special relativity. The paradox emerged gradually through discussions and objections raised by other physicists. Paul Langevin, a French physicist, popularized a version of the scenario in 1911, sparking debates that continued for decades. Some physicists insisted the situation was genuinely paradoxical and revealed a flaw in relativity. Others worked through the careful analysis and showed consistency. The debates were productive, sharpening understanding of what relativity actually claimed. There's a subtle point worth savouring as you drift towards sleep. Time dilation doesn't make one twin's experience wrong or illusory. Both twins experience completely real, valid time. The travelling twin genuinely lives through 10 years of meals, thoughts, heartbeats, and dreams. They don't feel time speeding up or slowing down. Subjective time feels normal throughout. What's strange is that their 10 years corresponds to their siblings' 60 years. Spacetime is built this way. Different paths through space-time accumulate different amounts of proper time, the time measured by a clock travelling along that path. Think of it like distance. 2 people driving from New York to Los Angeles might take different routes, one straight across the country, one meandering through Canada. They'd record different odometer readings despite starting and ending at the same locations. Nobody would call either driver's odometer wrong. They simply measured different paths. Similarly, the twins travel different paths through space-time and record different elapsed times. Neither is wrong. Space-time accommodates both. This geometric perspective would become clearer with Hermann Minkowski's reformulation, which we'll encounter soon. For now, rest in the realization that your experience of time isn't universal. Someone moving differently through the cosmos relative to you is aging at a different rate. They're not in a different timeline or parallel universe. They're in this universe, sharing this space-time, yet accumulating time differently than you. The night around you is silent. Perhaps you hear distant traffic, or a refrigerator hum, or the rhythm of someone else's breathing nearby. All these experiences feel simultaneous to you, but simultaneous is a local, approximate, convenient fiction. Across vast distances and relative motions, simultaneity dissolves into perspective. There's a humility in that, and perhaps a strange comfort. You're not the center of cosmic time. You're a traveler through space-time, accumulating your own proper time along your own world line, sharing the universe with travelers whose world lines interweave and diverge in ways your everyday intuition cannot capture. Here's something that might keep you awake for another few minutes, though I promise to make it gentle. When you move at extreme speeds, you don't just experience time differently. Space itself transforms. Objects compress in their direction of motion, becoming shorter than they really are, though that word really is doing more work than it deserves. Length contraction follows inevitably from Einstein's postulates, just as time dilation does. If moving clocks run slow and the speed of light must remain constant for all observers, then moving measuring sticks must shorten. The mathematics demands it. The universe obliges. Imagine you're watching a spaceship fly past at 86% of light speed, a velocity chosen because the Lorentz factor is exactly 2 at this speed, making the math tidy. From your stationary perspective, the ship appears compressed to half its rest length. A ship that measures 100 meters long when parked appears only 50 meters long while zooming past. This compression affects only the dimension parallel to motion. The ship's height and width remain unchanged. Now climb aboard mentally. You're on the ship, floating in your cabin, looking around. Everything appears perfectly normal. Your cabin is its full length. Your equipment hasn't shrunk. Your own body hasn't compressed. Yet when you look out the window at the universe rushing past, everything outside appears shortened in the direction of motion. Planets become squashed ellipsoids. Distant stars appear closer together in the forward direction. Space itself seems compressed from your perspective. Neither view is wrong. This is the central, counterintuitive message of relativity. There's no privileged reference frame that reveals the true lengths of things. Length, like time, depends on relative motion. The ship is simultaneously 50 meters from your stationary perspective and 100 meters from its own perspective, and both measurements are equally valid. You might wonder how something can be two lengths at once. The answer involves recognizing that length is a more complicated concept than everyday experience suggests. When you measure a stationary object's length, you can take your time, place a ruler alongside it, note the positions of both ends whenever convenient. But when measuring a moving object, you must note where both ends are at the same instant. And as we've already established, the same instant depends on your reference frame. Here's where it gets deliciously weird. The ship's length contraction is intimately connected to the relativity of simultaneity. From your stationary perspective, the ship's front end and rear end don't exist at the same moment in the ship's reference frame as they do in yours. You're measuring a kind of cross-section of the ship's existence through space-time, and that cross-section is shorter than the cross-section the ship would measure of itself. Don't strain to visualize this clearly. Even physicists who work with relativity daily find their intuitions rebelling. The human brain evolved to track medium-sized objects moving at medium speeds on the African savanna. It developed no need for relativistic intuition. Accepting that length is relative requires fighting millions of years of evolutionary training. Let's ground this in an experimental reality. Particle accelerators regularly produce particles travelling at 99.9999% of light speed. At such speeds, the Lorentz factor is roughly 707. From the laboratory's perspective, A particle beam travelling through a 1 kilometre pipe takes a certain time to traverse it. From the particle's perspective, that pipe appears compressed to about 1.4 metres. The particle crosses what seems like a very short distance, while the laboratory measures it crossing a very long one. Yet both measure the particle travelling at 99.9999% of light speed. The mathematics is consistent. The universe doesn't contradict itself. It just operates on principles stranger than everyday life reveals. Here's an amusing historical quirk. The idea of length contraction predates Einstein. George Fitzgerald and Hendrik Lorentz proposed it independently in the 1890s as an explanation for the Michelson-Morley experiment's null result. They imagined that objects physically contracted when moving through the ether, squished by some mechanical interaction with the invisible medium. This contraction would exactly compensate for expected light speed variations, hiding the ether's presence. It was a clever workaround, preserving Newtonian intuitions at the cost of introducing an unobservable effect. Einstein transformed this mechanical hypothesis into something fundamentally different. In his framework, there is no ether, no physical squishing. Length contraction emerges from the structure of spacetime itself, from how different observers slice spacetime into space and time components. The same mathematics, completely different interpretation. This distinction matters because Einstein's version makes clear that length contraction is reciprocal. You see my spaceship as shortened. I see your planet as shortened. Neither observation is more fundamental. Lorentz's mechanical contraction would have been one-sided, an absolute effect happening to objects moving through the ether. Historians still argue about how much credit Lorentz and Fitzgerald deserve for special relativity. They had the equations, they lacked the conceptual revolution. Some scholars suggest they couldn't abandon the ether because it was too deeply embedded in their worldview, and giving it up would have felt like abandoning physics itself. Einstein, younger and less invested in the old frameworks, could let go more easily. You're lying still, of course. Your body isn't experiencing measurable length contraction relative to your bed. But there's something poetic in recognizing that if you could somehow watch yourself from a passing cosmic ray's perspective, you'd appear compressed, flattened in one dimension, a squished version of yourself rushing through the cosmos at nearly light speed. Perspective matters. The universe looks different depending on where you stand in it. As drowsiness settles deeper, let go of the need to visualize perfectly. Length contraction is real, measured, confirmed by countless experiments. Whether it matches any picture in your head is almost irrelevant. The universe doesn't owe us intuitive explanations. It offers equations that work. Tonight, let that be enough. 2 years after Einstein's miracle year, a German mathematician made a comment that would reshape how physicists think about spacetime forever. Hermann Minkowski had actually been one of Einstein's teachers at the Swiss Federal Polytechnic in Zurich, and hadn't thought much of the young student. Einstein, for his part, had skipped many of Minkowski's mathematics lectures, considering them unnecessarily abstract. In 1907, Minkowski got a measure of intellectual revenge. Henceforth, space by itself, and time by itself, are doomed to fade away into mere shadows, Minkowski declared in a famous lecture, and only a kind of union of the two will preserve an independent reality. This was no poetry. Minkowski had recognized that special relativity's mathematics became simpler and more elegant when treated geometrically. Instead of viewing time and space as separate entities that transformed peculiarly during motion, he proposed treating them as a single four-dimensional structure, space-time. You're familiar with three-dimensional space. You can point forward, backward, left, right, up, down. 3 independent directions, 3 numbers needed to specify a location. Minkowski added a 4th dimension, time. Now specifying an event, a location plus a moment, required 4 numbers. Not 3 numbers for where, and then 1 number for when, but 4 numbers for where when, inseparably. This sounds like a bookkeeping trick, and at first Einstein dismissed it as exactly that. Since the mathematicians have invaded the theory of relativity, he reportedly grumbled, I do not understand it myself anymore. He would change his mind. The 4-dimensional perspective would prove essential for general relativity, his later masterpiece. Here's the key insight. In ordinary 3-dimensional space, you can rotate your coordinate system. What one person calls forward, another might call diagonally left. But distances between points remain unchanged. No matter how you orient your axes, the distance from your bed to your door stays the same. Mathematicians call this property invariance under rotation. Rotation mixes up the 3 spatial directions but preserves the fundamental geometry. Minkowski realized that special relativity's transformations between moving observers resembled rotations, but in 4-dimensional spacetime rather than 3-dimensional space. When you change from a stationary reference frame to a moving one, you're performing a kind of rotation that mixes space and time together. What I call purely spatial distance, you might call partly spatial, partly temporal. What I call simultaneous events, you might call events at different times. This mixing explains the strangeness we've encountered. Time dilation, length contraction, and the relativity of simultaneity all emerge naturally from the geometry of this 4-dimensional structure. They're not bizarre rules tacked onto reality, but inevitable consequences of space-time's shape. But Minkowski's spacetime isn't quite like ordinary 4-dimensional space. There's a crucial difference in how distances work. In regular space, the Pythagorean theorem tells you that distance squared equals x squared, plus y squared plus z squared, all positive terms added together. In spacetime, the analogous quantity, called the interval, involves a subtraction. The interval squared equals time squared, times the speed of light squared minus x, squared minus y squared minus z squared. That minus sign changes everything. It means space-time has a fundamentally different geometry than ordinary space. Mathematicians call it hyperbolic geometry, or more specifically, Minkowski geometry. The minus sign creates a distinction between time-like, space-like, and light-like separations, distinctions that don't exist in ordinary space. 2 events are time-like separated if a traveller could attend both by moving slower than light. They're space-like separated if no signal, even travelling at light speed, could connect them. They're light-like separated if light could just barely reach from one to the other. This classification is absolute. All observers agree regardless of their motion. The geometry preserves it. Here's a quirky consequence. In ordinary space, the shortest path between 2 points is a straight line. In Minkowski spacetime, the longest proper time between 2 events is achieved by a straight world line, a path of constant velocity, no acceleration. Any other path involving accelerations and direction changes accumulates less proper time. This is the twin paradox again, now explained geometrically. The travelling twin takes a bent path through space-time. The stationary twin takes a straight path. The straight path accumulates more time. Geometry makes the asymmetry obvious. Einstein initially resisted this geometric perspective, preferring algebraic and physical arguments. But as he struggled to extend special relativity to include gravity, a struggle lasting nearly a decade, he came to appreciate Minkowski's insight. The mathematics of curved spacetime built directly on Minkowski's flat spacetime foundation. Without the geometric reformulation, general relativity might never have emerged in recognizable form. Tragically, Minkowski never saw general relativity completed. He died of appendicitis in January 1909, less than 2 years after introducing spacetime to the world. He He was 44. Historians sometimes wonder how physics might have developed differently had he lived longer. Would he have contributed to general relativity's development? Would he have shaped quantum mechanics, which was then in its infancy? We'll never know. What we do know is that his four-dimensional perspective became standard. Today, physicists think in space-time instinctively. Particles trace world lines through it. Fields spread across it. Causality and the speed of light emerge from its geometry. The block universe, a philosophical interpretation we'll explore later, treats space-time as a single, eternal, unchanging structure, where past, present, and future all exist equally. You're embedded in this structure right now, tracing your world line through space-time as Earth rotates and orbits, and the solar system drifts through the galaxy. Every heartbeat, every breath, every thought advances you along your path. You cannot stop. You cannot step outside. You can only follow your world line into the future that space-time holds for you. Let that image carry you deeper towards sleep. You're not a passenger in time watching it flow past. You're a pattern in space-time, extended through dimensions you can't directly perceive, heading toward tomorrows that, in some interpretations, already exist, waiting for your world line to reach them. Special relativity was beautiful. It was revolutionary. It was experimentally confirmed in every domain it addressed, and Einstein knew it was incomplete. Like a sculptor who's finished one figure and sees the marble for the next, he understood that gravity remained outside the framework, awkward and unresolved. Newton's gravity worked spectacularly well for practical calculations. It described planetary orbits, tides, falling apples, everything engineers needed. But it conflicted with special relativity in a fundamental way. It acted instantaneously. In Newton's framework, if the sun suddenly disappeared, Earth would instantly feel the gravitational change and fly off in a straight line. No delay. Information about the sun's disappearance would travel infinitely fast. Special relativity forbids this. Nothing, no signal, no influence, no information can travel faster than light. If the sun vanished, Earth should keep orbiting normally until light-speed signals could bring news of the catastrophe, roughly 8 minutes later. Newton's instantaneous gravity violated relativistic causality. Einstein needed a new theory of gravity, one compatible with special relativity's speed limit. The search consumed him for nearly a decade, from roughly 1907 to 1915. Friends and colleagues watched him struggle, occasionally producing promising ideas that led nowhere, sometimes despairing of ever finding the answer. The breakthrough came through a thought experiment, another instance of Einstein's remarkable ability to extract deep physics from simple imaginary scenarios. Imagine you're in an elevator, or, as Einstein put it, a large box, with no windows, completely isolated from outside observation. The box begins accelerating upward. You feel pressed against the floor. If you drop a ball, it falls toward the floor. Now consider, can you distinguish this accelerating box from one sitting stationary in a gravitational field? If the box were resting on Earth's surface, you'd feel pressed against the floor. If you dropped a ball, it would fall toward the floor. The experiences are identical. Einstein proposed that they weren't just similar, they were fundamentally indistinguishable. Acceleration and gravity, he claimed, were equivalent. No local experiment could tell them apart. This equivalence principle became the foundation of general relativity. The implications unfold gradually. If acceleration and gravity are equivalent, then anything true about accelerated motion should have gravitational counterparts. Consider light in an accelerating spaceship. If you shine a flashlight horizontally across the ship's cabin while the ship accelerates upward, the light beam will curve downward relative to the cabin, because during the time the light crosses the cabin has accelerated upward moving the far wall slightly higher than where the light was aimed. By the equivalence principle, light must also bend in a gravitational field. Gravity affects light. This was a shocking prediction. In Newtonian physics, light has no mass. It shouldn't respond to gravity at all. Einstein's theory said otherwise. Here's where spacetime's geometry becomes essential. Einstein, now fully appreciating Minkowski's perspective, realized that gravity isn't a force in the traditional sense. It's a curvature of spacetime itself. Massive objects like the sun don't reach out and pull other objects. Instead, they bend the spacetime around them. Other objects, planets, comets, even light beams, follow the straightest possible paths through this curved geometry. Those paths curve toward the massive object, mimicking the effects of gravitational attraction. This reimagining is profound. In Newton's universe, space is flat and empty, and gravity is a mysterious force acting at a distance. In Einstein's universe, space is curved and dynamic, and what we call gravity is simply geometry. Objects move freely without forces along geodesics, the curved space equivalent of straight lines. Think of walking on Earth's surface. You set out due north and walk in a straight line, never turning. Eventually you return to your starting point, having circumnavigated the globe. Your path was straight in two-dimensional terms. You never deviated left or right. But Earth's surface is curved, so your straight path loops back. Similarly, planets orbiting the Sun are following straight paths through space-time. They're not being pulled by any force. Space-time itself curves around the Sun, and straight paths through that curved geometry are orbits. This geometric perspective explains why gravity affects all objects equally, regardless of mass or composition. A feather and a bowling ball dropped in vacuum fall at exactly the same rate. In Newton's framework, this was a strange coincidence. Gravitational force happens to be proportional to mass, which cancels the mass in the acceleration formula. In Einstein's framework, it's obvious. Both objects follow space-time geodesics, and geodesics don't depend on the object's properties at all. Geometry is geometry for everyone. Historians still argue about whether Einstein could have developed general relativity without Minkowski's geometric language. Some suggest the conceptual leap was Einstein's alone, with the mathematics being just a tool. Others note that Einstein struggled precisely because he initially resisted the geometric perspective and only progressed rapidly after embracing it. Perhaps, as with many discoveries, no clean separation exists between conceptual insight and mathematical expression. Einstein's path to the final equations was tortuous. Collaborating with mathematician Marcel Grossmann, he explored various mathematical frameworks for curved spacetime. He published preliminary versions that turned out to be wrong. He made errors. He backtracked. The correct field equations emerged in November 1915, presented in a series of lectures to the Prussian Academy of Sciences. Physicist David Hilbert may have independently derived equivalent equations around the same time, another priority dispute that historians continue to examine. What matters for tonight is the result, a theory describing gravity as curved space-time, making predictions that differed from Newton's in subtle but measurable ways. The cosmos had become stranger and more beautiful than Newton's clockwork had ever suggested. You've probably seen the image, a bowling ball sitting on a stretched rubber sheet, creating a dip that smaller balls roll toward. This is how countless textbooks, documentaries, and science communicators explain curved space-time. It's intuitive, it's visual, and it's almost completely misleading. The bowling ball analogy has seduced generations of students, but it fails in ways that matter. Understanding why it fails illuminates what space-time curvature actually means. First problem, the analogy uses gravity to explain gravity. Why does the small ball roll toward the bowling ball's dip? Because gravity, regular, three-dimensional, Newtonian gravity, pulls it down the slope. You're smuggling in the very thing you're trying to explain. A truly geometric explanation shouldn't need an external gravitational field to make sense. Second problem, the rubber sheet is two-dimensional space, and the dip extends into a third spatial dimension. This suggests that space-time curvature requires some extra dimension for space-time to curve into. It doesn't. General relativity describes intrinsic curvature that exists within the dimensions themselves, not by bending into some higher dimension. The mathematics handles this perfectly, but it's counterintuitive for brains accustomed to visualizing surfaces from outside. Third problem, the bowling ball analogy shows only space being curved, not space-time. It's static. Nothing moves. But the really interesting effects, gravitational time dilation, orbital dynamics, the behavior of light, emerge specifically from the time component of space-time curvature. A purely spatial image misses the crucial point. So what does space-time curvature actually mean? Imagine you and a friend standing on Earth's equator 10 meters apart, both facing due north. You begin walking forward, maintaining perfectly parallel paths, neither veering left nor right. Yet as you approach the North Pole, you'll find yourselves converging. By the time you reach the pole, you'll collide. Your initially parallel paths intersected. On a flat plane, parallel lines never meet. On a curved surface like Earth's, they can. This is what curvature means mathematically. It affects how parallel paths behave. Space-time curvature means that world lines that start parallel, objects initially moving together with the same velocity, can converge or diverge. Consider two astronauts drifting freely in space, far from any planets. They float motionless relative to each other, separated by 10 meters. In flat space-time, they'd remain 10 meters apart forever. No forces act on them. Inertia carries them forward. Now place a massive planet beneath them. Each astronaut follows a geodesic through curved space-time, the straightest possible path through that geometry. But the geodesics converge toward the planet's center. Without feeling any force, without detecting any change in their motion, the astronauts drift closer together. An observer might say, gravity is pulling them toward the planet, but in Einstein's framework they're simply following straight paths through curved geometry, and those paths happen to converge. This convergence of geodesics is what we experience as gravitational attraction. It's not a force applied to objects, it's the shape of space-time itself, guiding motion geometrically. Space-time curvature also affects time, and this is arguably more important than spatial effects. Near a massive object, time runs slower. Clocks tick fewer times per interval compared to clocks farther away. This isn't an analogy or approximation. It's precisely what the equations say, and it's precisely what experiments confirm. When you stand on Earth's surface, your feet are closer to Earth's center than your head. Your feet experience slightly stronger space-time curvature. Time passes slightly slower for your feet than for your head. The difference is absurdly small, about 90 billionths of a second over a lifetime, but it's real and measurable with modern atomic clocks. Here's a historical quirk worth mentioning. Einstein initially proposed a version of general relativity that made correct predictions for the bending of light by the sun, but wrong predictions for other phenomena. He published in 1911, 4 years before the final theory. When he realized his error and rederived the equations, he found that the light bending should be twice what his earlier, incorrect theory predicted. This doubling would later provide a crucial test distinguishing general relativity from alternative theories. Historians still argue about how close Einstein came to abandoning the quest during those difficult years between 1911 and 1915. Letters reveal frustration, self-doubt, dead ends pursued and discarded. The triumphant story we tell in retrospect smooths over years of confusion and error. Science advances messily, even for geniuses. Perhaps the deepest conceptual shift is this. In Newton's physics, space and time formed a fixed stage on which matter performed. The stage never changed. Matter moved around on it, but the background was static and absolute. In Einstein's general relativity, the stage itself becomes a character in the drama. Matter tells space-time how to curve. Curved space-time tells matter how to move. The relationship is reciprocal, dynamic, evolving. This means the universe can't have a fixed, unchanging geometry. If matter moves, space-time curvature changes. The equations describe a dynamically evolving geometry that responds to its contents. This opened possibilities Newton could never have imagined. An expanding universe, black holes, gravitational waves. The static cosmos became a living, breathing, changing thing. As your thoughts soften and your muscles relax, let go of the rubber sheet. It served as a stepping stone, nothing more. The real space-time isn't a surface you could touch or see. It's the fabric of existence itself, curved and twisted by the presence of mass and energy, guiding everything, including you, along paths determined by geometry rather than force. The year is 1919. Europe is still reeling from the catastrophe of World War I. Empires have collapsed. Millions are dead. The old certainties of Victorian civilization lie shattered. Into this exhausted world comes news from a British scientific expedition that observed a total solar eclipse from the island of Principe off the coast of West Africa. What they found would make Albert Einstein the most famous scientist on Earth overnight. The expedition, led by astronomer Arthur Eddington, set out to test Einstein's prediction that starlight should bend as it passes near the Sun. General relativity claimed that massive objects curve space-time, and light follows those curves. During a total eclipse, when the Sun's blinding disk is blocked by the Moon, stars near the Sun's apparent position become visible. If space-time bends around the Sun, those stars should appear slightly displaced from their normal positions, shifted outward, away from the Sun, by a precise amount Einstein's equations predicted. Eddington was one of the few British scientists who had studied Einstein's work during the war, when communication between British and German academics was practically impossible. He understood general relativity's significance and championed it despite the political tensions that made admiring a German theorist controversial. The expedition faced challenges. Weather on Principe was poor. Clouds threatened to ruin the observations. Equipment malfunction plagued the second team stationed in Sobral, Brazil. Analysing the photographic plates required painstaking measurements with considerable uncertainty. Later historians would note that Eddington's results, while consistent with Einstein's prediction, had error bars large enough that they didn't definitively exclude Newton's theory or other alternatives. But Eddington believed, and he announced his results triumphantly. The measured deflection matched Einstein's prediction closely enough to declare victory. Newton had predicted some bending based on treating light as particles with mass, half of what Einstein's theory predicted. The observations favoured Einstein's larger deflection. The newspapers went wild. "Revolution in science," declared the Times of London. "New theory of the universe, Newtonian ideas overthrown." Einstein's face appeared on front pages worldwide. The shy, rumpled physicist became a celebrity, asked for autographs, mobbed by crowds, invited to lecture tours. Why such extraordinary public reaction? Partly it was the romance of the story, a pure intellectual achievement lifting humanity's spirits after years of mechanized slaughter. Partly it was the exotic appeal of eclipse expeditions to remote islands, and partly perhaps it was hunger for news that transcended national conflicts, for evidence that human cooperation in pursuit of truth could survive hatred and war. Here's a quirky historical detail. Eddington was a Quaker and conscientious objector during the war. He avoided prison partly because influential scientists argued he was needed to pursue important astronomical work. The eclipse expedition served in a sense as his national service contribution. That a pacifist scientific work would validate a German's theory, announced jointly by British and German institutions, carried symbolic weight in those raw post-war months. Historians still argue whether Eddington's analysis was objective or whether his commitment to Einstein's theory biased his interpretation of ambiguous data. Re-examinations of the original plates have continued for decades, with varying conclusions. The consensus today is that the 1919 measurements, while pointing in the right direction, weren't precise enough to definitively confirm general relativity over all alternatives. Later eclipse measurements and other tests provided much stronger confirmation. But none of that mattered for Einstein's fame. The cultural moment had arrived. He became the archetype of the revolutionary genius, the thinker who overthrew common sense and revealed a stranger reality beneath appearances. His wild hair, his casual dress, his violin playing, his pithy quotes about imagination, all became part of a public image that persists today. Light bending is now measured with exquisite precision, not just during eclipses but through gravitational lensing, the phenomenon where massive galaxies and clusters bend light from more distant objects behind them. Space telescopes have captured stunning images of galaxies whose light has been warped into arcs and rings by intervening mass. What Eddington glimpsed faintly in 1919 has become a routine astronomical tool for probing the universe's structure and measuring dark matter distributions. The conceptual importance runs deeper than practical applications. Light bending confirms that gravity isn't a force acting at a distance. It's space-time itself, curved and shaped, guiding everything that travels through it. Light follows geodesics. Planets follow geodesics. You follow geodesics through space-time with every moment of your existence. The geometry is indifferent to what travels through it. The geometry is the story. If you were a photon departing a distant star, you wouldn't know or care about the sun waiting to bend your path. You'd simply travel straight, absolutely straight in terms of space-time geometry. But that straight path, passing near the sun's curved space-time, would arc gently. You'd arrive at Earth slightly displaced from where a naive straight-line extrapolation predicted. Future scientists would measure your displacement and confirm that space-time curves. As you settle into deeper stillness, consider that the light entering your room right now has travelled straight paths through space-time. Photons from your ceiling lamp traverse negligible curvature. Earth's gravity is weak and your room is small. But photons from distant stars grazing past massive objects on journeys spanning millions of years have traced out the universe's geometry. Their arrival at your eyes carries information about the curvature they navigated. You're bathing in evidence of curved space-time every time you see the stars, even tonight, even in darkness, even as your eyes close and sleep approaches, the cosmic geometry surrounds and permeates you. Einstein's equations had an embarrassing prediction lurking within them, one that Einstein himself found too absurd to accept. When enough mass concentrates in a small enough region, space-time curvature becomes so extreme that nothing, not even light, can escape. The region becomes a cosmic trap, a one-way door leading only inward, never outward. We call them black holes now, though that term didn't emerge until 1967, coined by physicist John Wheeler. For decades they remained mathematical curiosities, taken seriously by few physicists, dismissed even by Einstein himself. The first person to derive what we now recognise as a black hole solution was Karl Schwarzschild, a German astronomer serving on the Eastern Front during World War I. In the trenches between battles, Schwarzschild worked through Einstein's field equations for the simplest possible case: a perfectly spherical, non-rotating mass. His solution revealed a peculiar radius, now called the Schwarzschild radius, at which space-time behaviour becomes singular. For the Sun, this radius is about 3 kilometres. For Earth, about 9 millimetres. If you compressed the Sun into a sphere smaller than 3 kilometres, Schwarzschild's solution implied that something strange would happen at that radius. Space-time itself would curve so severely that the roles of space and time would effectively swap. Inside the Schwarzschild radius, falling toward the centre becomes inevitable as moving forward in time. You cannot stop, you cannot hover, you cannot escape. Every path leads inward. Schwarzschild mailed his solution to Einstein in January 1916 and died a few months later, apparently from a rare autoimmune disease contracted in the field. He never knew the enormity of what he'd discovered. For decades, physicists assumed no physical process could create such extreme compression. Stars were held up by pressure, nuclear fusion, thermal energy, quantum effects. Surely no real star could collapse to such absurd density. The Schwarzschild solution was mathematically valid but physically irrelevant, or so the reasoning went. This view began changing in the 1930s when Subrahmanyan Chandrasekhar, a young Indian physicist, showed that white dwarf stars have a maximum mass. Above that limit, roughly 1.4 solar masses, electron pressure cannot support the star against gravity. Further calculations by Robert Oppenheimer and others demonstrated that neutron stars also have mass limits. Beyond these limits, nothing known could prevent collapse. Still, skepticism persisted. Einstein argued in a 1939 paper that black holes couldn't form through realistic physical processes. The mathematical singularity, he felt, must signal a breakdown of the theory rather than a physical reality. Nature surely wouldn't permit such extremity. But nature, it turns out, doesn't care what physicists find comfortable. By the 1960s, observations of quasars, impossibly luminous objects at cosmic distances, demanded energy sources far beyond what ordinary nuclear physics could provide. The most plausible explanation was gas falling into massive black holes, releasing gravitational energy as it spiraled inward. Theoretical work by Roger Penrose and Stephen Hawking demonstrated that gravitational collapse to singularities was mathematically inevitable under reasonable physical conditions, not a bizarre edge case. The name black hole captured popular imagination perfectly. These objects are black because light cannot escape, nothing to see, nothing to reflect back. And they're holes in some poetic sense, regions of space-time you can enter but never leave, doorways to oblivion. Here's a detail that captures the strangeness. If you fell into a black hole, you wouldn't notice crossing the event horizon, that boundary marking the point of no return. Space-time there isn't locally unusual. You'd experience no bump, no barrier, no sign that you'd passed the threshold. Only later, trying to escape, would you discover that all paths lead inward. Your light signals would be trapped. Your radio calls for help would spiral down with you. To an outside observer, you'd appear to freeze at the horizon, your image redshifting toward invisibility, never quite crossing, though from your perspective, you'd have fallen through long ago. Time dilation becomes infinite at the horizon from an outside perspective. An astronaut hovering just outside would age minutes while years passed on distant Earth. At the singularity itself, the point of infinite density at the centre, our equations break down entirely. General relativity predicts its own failure there, announcing that something beyond our current understanding happens when space-time curvature becomes truly extreme. Historians still argue whether black holes count as a prediction of general relativity or merely as a mathematical possibility that happened to be physically realized. Einstein's equations allow black hole solutions, but the equations don't require that nature produces them. It took decades of astronomical observation to confirm that nature does in fact create these monsters, and creates them abundantly. Nearly every galaxy harbours a supermassive black hole at its centre, millions or billions of times our Sun's mass. Stellar mass black holes pepper galaxies, remnants of collapsed massive stars. The universe is riddled with these gravitational traps. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole, or rather, of the glowing material swirling around one. The shadow in the centre, a dark circle against fiery orange, mark the black hole's silhouette. Einstein's equations predicted that shadow's size and shape. The match was precise. You drift now through a universe populated by objects Einstein doubted could exist. Millions of them, billions, hidden in every direction, bending light, swallowing stars, anchoring galaxies. Reality exceeded even the revolutionary theorist's imagination. Einstein's equations contained another prediction that Einstein himself rejected, only to be proven wrong decades later. Massive objects don't just curve spacetime. When they accelerate, they send ripples through the cosmic fabric, ripples that propagate outward at the speed of the light, carrying energy and information across the universe. We call them gravitational waves. Imagine spacetime as the surface of a pond. A massive object resting quietly creates a static depression, curved space-time around it. But if that object suddenly moves, accelerates, orbits, or collides with another, the disturbance spreads outward. Ripples race across the pond. Space-time itself oscillates, stretching in one direction while squeezing in the perpendicular direction, then reversing, oscillating like a drum membrane struck by cosmic hammers. Einstein derived these waves from his field equations in 1916 and 1918, but then spent years doubting whether they were real. The mathematical description was tricky. Early calculations suggested the waves might carry no energy, being mere coordinate artifacts, mathematical ghosts rather than physical phenomena. Einstein and others flip-flopped on the question for decades. As late as 1936, Einstein submitted a paper arguing that gravitational waves didn't exist, only to have it rejected by a referee who spotted errors in his reasoning. Einstein revised his view again. The resolution came through patient theoretical work showing that gravitational waves do carry energy and can in principle be detected, but the amounts involved are tiny. Even catastrophic cosmic events, supernovae colliding neutron stars, produce gravitational waves so weak that by the time they reach Earth, they stretch and squeeze distances by far less than the diameter of a proton. Detecting such infinitesimal effects required technology that wouldn't exist for half a century. The first indirect evidence came in 1974, when Russell Hulse and Joseph Taylor discovered a binary pulsar, two neutron stars orbiting each other, one emitting regular radio pulses. By timing these pulses with extraordinary precision, they could track the orbital period. Over years, the orbit shrank slightly. The neutron stars were spiraling together, losing energy. The rate of energy loss matched exactly what general relativity predicted from gravitational wave emission. The waves themselves weren't detected directly, but their effects were unmistakable. Hulse and Taylor shared the 1993 Nobel Prize for this work. Direct detection remained the goal. Beginning in the 1990s, scientists built LIGO, the Laser Interferometer Gravitational Wave Observatory, a pair of massive detectors in Louisiana and Washington state. Each detector consists of two perpendicular arms, each 4 kilometers long, with laser beams bouncing between mirrors at the ends. A passing gravitational wave would stretch one arm and squeeze the other, changing the interference pattern of the recombined lasers. The required sensitivity was absurd. detecting changes in arm length smaller than 1/10,000th the diameter of a proton. On September 14, 2015, both LIGO detectors registered a distinctive chirp, a signal sweeping upward in frequency, lasting about 1/5 of a second. Analysis revealed its origin. Two black holes, about 36 and 29 times our Sun's mass, had spiraled together and merged roughly 1.3 billion light-years away. In the final fraction of a second before merger, they orbited each other hundreds of times per second, releasing more energy and gravitational waves than all the stars in the observable universe were emitting in light at that moment. The announcement came in February 2016, exactly 100 years after Einstein first predicted gravitational waves. The confirmation capped a century of speculation, calculation, technological development, and persistence. Einstein's doubt had been misplaced. The waves were real. Since then, LIGO and its partner detectors have recorded dozens of gravitational wave events, black hole mergers, neutron star collisions, possibly other exotic sources. Each detection opens a new window on cosmic phenomena invisible to light-based astronomy. Gravitational waves penetrate dust clouds, escape from regions where light cannot, carry information from moments of cosmic cataclysm. Here's a quirky detail. The gravitational wave passing through Earth during that first detection stretched and squeezed distances by about 1/1,000,000th the width of a proton. The LIGO instruments measured this. Human technology reached a sensitivity threshold that seemed impossible decades ago. Einstein's abstract equations now manifest in laser interference patterns analysed by computers, confirming a prediction he himself doubted. Historians still argue whether Einstein deserves credit for predicting gravitational waves, given his wavering confidence in their existence. Scientific credit is a messy concept. Ideas evolve, intuitions prove wrong, equations outlive their creators' interpretations. What remains is the framework itself, a theory of curved, dynamic spacetime that predicted phenomena its author didn't fully trust. The universe ripples with gravitational waves right now. Massive objects throughout the cosmos are accelerating, orbiting, colliding, sending spacetime oscillations in every direction. Some pass through your body as you listen to these words, stretching and squeezing you by amounts too small for any sensation but real nonetheless. You're a tiny cork bobbing on a vast gravitational sea, moved by waves from events so distant their light has travelled billions of years to reach you. Your feet are aging more slowly than your head, right now. As you lie there, time passes fractionally faster for the neurons in your brain than for the bones in your toes. The difference is so minuscule that no subjective experience could ever detect it. Roughly 90 billionths of a second over an entire lifetime. Yet it's real, measurable, a consequence of Einstein's equations playing out in the gentle gravity of Earth. This is gravitational time dilation, distinct from the velocity-based time dilation of special relativity. Near massive objects, time runs slower. The closer you are to a mass, the more space-time curves, the more time slows. It's not that clocks malfunction or that some mechanical effect interferes with their workings. Time itself passes more slowly. Biological processes, chemical reactions, radioactive decays, everything ticks slower in stronger gravitational fields. The effect emerges directly from general relativity's mathematics. When Schwarzschild solved Einstein's equations for spherical masses, his solution contained a time component that varied with distance from the mass. Clocks closer to the centre run slow compared to clocks farther away. At Earth's surface, this effect is tiny but non-zero. At the surface of a neutron star, it's dramatic. At a black hole's event horizon, time dilation becomes infinite. From an outside perspective, time stops entirely. How do we know this isn't just theoretical speculation? Consider the Pound-Rebka experiment of 1959. Robert Pound and Glenn Rebka set up a gamma-ray source in the basement of a tower at Harvard University and a detector at the top, 22 meters higher. Gamma rays emitted from the source had a specific frequency determined by atomic physics. If time ran slower in the basement, where gravity was infinitesimally stronger, then the gamma rays should be blue-shifted by the time they reached the top. Their frequency increased slightly as they climbed out of the denser gravitational field. The predicted shift was about 2 parts in a million billion, fantastically small. Yet using the Mössbauer effect to achieve extraordinary frequency precision, Pound and Rebka measured exactly the predicted shift. Gravitational time dilation was real, measurable over a distance shorter than a football field. Later experiments pushed precision further. In 2010, scientists at the National Institute of Standards and Technology compared atomic clocks separated by just 33 centimeters of height. They measured time dilation between them. The higher clock gained about 90 billionths of a second per 79-year lifetime, confirming Einstein's prediction at tabletop scales. Here's a quirky application that grounds this in everyday technology. GPS satellites orbit roughly 20,000 kilometers above Earth. Their clocks experience weaker gravity than clocks on the surface, so general relativity predicts they run fast by about 45 microseconds per day. Meanwhile, their orbital velocity causes special relativistic time dilation, making their clocks run slow by about 7 microseconds per day. The net effect: satellite clocks gain roughly 38 microseconds daily compared to ground clocks. 38 microseconds sounds trivial, but GPS determines position by timing signals with nanosecond precision. 38 microseconds of uncorrected drift would accumulate positioning errors of roughly 10 kilometers per day. Your GPS would be useless by lunch. Engineers must apply relativistic corrections to keep the system functional. Every time you navigate somewhere, you're depending on Einstein's equations being correct. Historians still argue about whether Einstein anticipated practical applications of his theory or viewed it purely as fundamental physics. His writings suggest he cared primarily about understanding nature, not building technologies. That his abstract equations would enable satellite navigation, gravitational wave astronomy, and precision timekeeping might have amused him. The universe's deep structure turns out to have engineering consequences. Consider the implications for cosmic exploration. If humans ever travel to massive objects, neutron stars, the vicinity of black holes, they'll experience significant time dilation. An astronaut hovering near a neutron star's surface would age slower than their colleagues in distant orbit. Mission durations would depend on where crew members station themselves. Time would flow at different rates for different team members, making coordination peculiar. Near black holes, the effects become extreme. The movie Interstellar dramatized this. Characters visiting a planet near a massive black hole experienced hours while decades passed for their orbiting colleague. This scenario is physically plausible, not science fiction but science fact extrapolated. General relativity permits exactly such extreme time differentials. You might wonder if gravitational time dilation could enable a kind of time travel, specifically travel into the future. In a sense, yes. If you descended toward a neutron star, hovered there for what felt like a year, then climbed back up, you might find that 10 years or a century had passed elsewhere. You'd have fast-forwarded through others' lives, arriving in their future having aged minimally yourself. This isn't the time travel of science fiction, where you jump backward to change history. It's one-way travel forward, achieved simply by visiting regions where time flows differently. The philosophical implications are dizzying, but you don't need to grasp them tonight. What matters is the basic insight. Time is local. The rate at which time passes depends on where you are and how you're moving. There's no universal clock ticking away in some cosmic control room. there's only the tapestry of space-time, with each point having its own local flow, its own proper time accumulating along every world line. Your world line threads through Earth's gentle gravity well, accumulating time at a rate determined by your position and motion. The world line of an astronaut on the International Space Station accumulates time slightly differently. They age about 0.01 seconds less per year than you do, a combination of velocity effects, slowing their time, and altitude effects, speeding their time, with velocity winning slightly. None of this makes one person's time more real than another's. All time is equally real. The universe just doesn't enforce synchronization. Time is flexible. Time is local. Time bends. Rest in that flexibility. Let your local time carry you towards sleep, flowing at its own pace, unique to your position in the cosmos. The modern world runs on precise timing, and precise timing runs on Einstein. Your phone, your car's navigation, your financial transactions, the electrical grid, air traffic control, all depend on synchronization technologies that would fail catastrophically without relativistic corrections. GPS is the most familiar example, but it's worth exploring in detail because it illustrates how abstract physics becomes concrete infrastructure. The global positioning system consists of at least 24 satellites orbiting Earth at roughly 20,000 kilometers altitude, completing orbits every 12 hours. Each satellite carries atomic clocks and continuously broadcasts signals containing its position and the precise time of transmission. Your GPS receiver picks up signals from multiple satellites, notes the arrival times, and calculates how far each signal travelled based on the time delays. With distances to several satellites, triangulation determines your position. The entire system depends on timing accuracy. Light travels about 30 centimeters per nanosecond. If satellite clocks are off by even a few nanoseconds, position errors of meters result. The system aims for accuracy within a few meters, requiring timing precision of tens of nanoseconds. Einstein enters through both special and general relativity. The satellites move at about 14,000 kilometers per hour relative to ground, causing special relativistic time dilation. Their clocks tick slower by about 7 microseconds per day from our perspective. Simultaneously, the satellites experience weaker gravity than ground clocks, causing general relativistic time speedup about 45 microseconds per day. The net effect is that satellite clocks run fast by about 38 microseconds daily compared to ground clocks. Left uncorrected, this would destroy positioning accuracy within hours. The solution: satellite clocks are deliberately set to tick at a slightly slower frequency before launch, pre-compensating for the relativistic speed-up they'll experience in orbit. Additionally, ground-based corrections are uploaded regularly to account for remaining drift and other effects. Here's a historical tidbit that physicists love. When GPS was being designed in the 1970s, some engineers doubted whether relativistic effects would matter. The system was built with the capability to include or exclude relativistic corrections, allowing empirical testing. The corrections proved absolutely essential. Without them, positioning errors grew at about 10 kilometers per day. Nature doesn't negotiate with skeptical engineers. Beyond GPS, precise timing underlies technologies you might not associate with Einstein. Financial markets depend on synchronized timestamps for transactions. High-frequency trading algorithms exploit millisecond advantages. Timing disputes can involve billions of dollars. The electrical grid requires synchronized measurements across vast distances to balance supply and demand. Telecommunications networks coordinate data transmission using precisely shared time references. All these systems ultimately trace their timing to atomic clocks, devices that measure the oscillations of atoms, typically cesium or rubidium. Atomic clocks achieve stabilities of parts in 10 billion billion. so precise that relativistic effects from altitude differences of centimeters become measurable and relevant. The most precise clocks today use optical frequencies, measuring oscillations of atoms at visible light frequencies rather than microwave frequencies. These optical clocks lose or gain less than 1 second over the age of the universe. At such precision, gravitational time dilation from a few centimeters of height difference becomes significant. You could detect whether your clock was placed on the floor or a tabletop simply from the time it kept. Here's a quirky frontier application: relativistic geodesy. By comparing precise clocks at different locations, scientists can measure height differences through gravitational time dilation. Clock A runs slightly slow compared to clock B. A must be lower in Earth's gravity well. This provides an independent method for mapping Earth's gravitational field, complementing satellite and ground-based measurements. Einstein's theory becomes a surveying tool. Historians still argue about whether the practical payoffs of relativity would have surprised Einstein. His motivations were philosophical and aesthetic. He wanted to understand how the universe worked, not build better navigation systems. But physics has a way of generating unexpected applications. Quantum mechanics, developed around the same time, now underlies all of electronics. Relativity, perhaps less obviously, underlies all precise timekeeping. Consider the deeper message. The universe's fundamental structure isn't separate from everyday life. The same space-time geometry that black holes warp to extremes also warps subtly around Earth, affecting the clocks that run your civilization. You don't need to understand the equations to benefit from them. The GPS satellites don't care whether you comprehend their relativistic corrections. They just work, silently, constantly, translating Einstein's century-old insights into the convenience of knowing where you are. Tonight, wherever you are, satellites overhead are broadcasting time signals corrected for effects Einstein predicted. Your phone might be listening, updating its clock, refining your location. The invisible infrastructure of space-time geometry hums along, indifferent to whether anyone appreciates its elegance. You're embedded in a technological civilization that depends on understanding how time bends. Not everyone needs to know the details, but somewhere, engineers and physicists are tending the systems, applying the corrections, keeping the modern world synchronized. They're the inheritors of Einstein's legacy, translating abstraction into infrastructure. As your thoughts slow and your body relaxes, let that knowledge settle somewhere comfortable. The universe is strange, but humanity has learned enough of its strangeness to build wonders. You rest within those wonders tonight, time flowing past you at your local rate. Einstein's equations quietly shaping the world you'll wake into tomorrow. Here's a thought that might keep philosophers awake at night, even as it lulls you towards sleep. If space-time is a four-dimensional structure, and all points in it are equally real, then perhaps the past hasn't vanished and the future hasn't yet to exist. Perhaps they're all there, spread out across eternity, and our experience of now moving forward is simply how consciousness navigates a structure that doesn't actually change. This interpretation is called the block universe, and it follows naturally from Minkowski's four-dimensional space-time. Think of the universe not as a three-dimensional stage where things happen over time, but as a four-dimensional sculpture that simply exists, complete, eternal, unchanging. Every moment of history, from the Big Bang to the heat death of the cosmos, is present somewhere in this block. We don't witness time passing. We're embedded at particular locations in the block, experiencing the local slice as now. From this perspective, the Battle of Waterloo isn't gone. It's located at particular space-time coordinates, as real as the events happening now. Your childhood didn't disappear. It exists at earlier coordinates along your world line. Your death, whatever moment that will be, already exists at later coordinates. Nothing truly passes. The block just is. This might sound like mystical speculation, but it emerges from taking relativity's geometry seriously. Remember, different observers disagree about simultaneity. What I call now across the universe isn't the same as what you call now if you're moving relative to me. We slice the block differently. There's no single, objectively correct present moment stretching across space-time. Now is observer-dependent. If now were objectively special, if there were a real, universal present moment, then observers should agree on what it contains. They don't. Relativity forbids it. So either there's no objective present, or there are infinitely many equally valid presents, one for each possible state of motion. Either way, the past and future seem to have the same ontological status as the present. They're all real regions of the space-time block. Here's a quirky consequence. In the block universe, the future already exists, not as a vague potentiality, but as concrete determinate events. The coffee you'll drink tomorrow morning, the words you'll speak, the decisions you'll make, all are located somewhere ahead along your world line, as fixed as your breakfast last Tuesday. Does this mean free will is an illusion? Philosophers have argued this for centuries, and relativity adds new dimensions to old debates. Some argue that block universe determinism is compatible with meaningful choice, that your decisions are part of what determines the block structure, even if the structure is eternal. Others see deep tension, arguing that genuine agency requires an open future, not a sculpted one. Einstein himself seemed drawn to the block universe view. After his lifelong friend Michel Besso died in 1955, just weeks before Einstein's own death, Einstein wrote to Besso's family, "Now he has departed from this strange world a little ahead of me. That signifies nothing." For us believing physicists, the distinction between past, present and future is only a stubbornly persistent illusion. This wasn't grief speaking carelessly. Einstein consistently expressed views suggesting he took the block universe seriously. Time's passage in this picture is psychological, not physical. The block simply exists. Our minds move through it, or seem to, but the motion is appearance, not reality. Historians still argue whether Einstein's philosophical views on time were rigorous conclusions from his physics or personal intuitions shaped by his physics. He wasn't a professional philosopher, and his statements sometimes conflate different issues. But his words capture something profound. Relativity challenges not just our practical understanding of clocks, but our deepest assumptions about what time is. Not all physicists accept the block universe. Some interpretations of quantum mechanics seem to require an open future, where events are genuinely undetermined until observed. The measurement problem, what happens when a quantum superposition collapses to a definite outcome, might involve something block universes can't accommodate. The tension between relativity and quantum mechanics, which we'll explore later, surfaces here too. Others argue that the block universe's determinism is illusory, that while the mathematical structure is four-dimensional, the physical ontology might still privilege the present. These debates remain unresolved. Physicists and philosophers continue arguing, and no experiment has definitively settled the matter. For tonight's purposes, the block universe offers a strange comfort. If your past exists eternally in the space-time structure, then your memories aren't just neural traces. They're pointing towards something real, something still there in its proper location. Your childhood self doesn't vanish. They're located earlier along your world line, frozen in space-time amber. The people you've lost aren't truly gone. They exist at the coordinates where their world lines still thread. This might sound like mysticism dressed in physics language. Perhaps it is. Or perhaps physics reveals that reality is stranger than everyday intuition, and mysticism has been groping toward truths that equations can articulate more precisely. Either way, the block universe waits, You're moving through it, or seeming to, tracing your world line toward coordinates you call tomorrow. Rest in that motion. The block holds all things, all moments, all possibilities already actualized. For nearly a century, physicists have known that two of our most successful theories fundamentally disagree about the nature of reality. General relativity describes space-time as smooth, continuous, curved by mass and energy. Quantum mechanics describes the subatomic world as probabilistic, discrete, fuzzy. Where they overlap, at extremely small scales and extremely high energies, neither works properly. This conflict is the deepest unsolved problem in fundamental physics. General relativity treats space-time as a classical field, meaning it has definite values at every point. Curvature here, flatness there, specific geometry everywhere. There's no uncertainty in the metric, the mathematical object describing space-time's shape. You can ask, what's the curvature at this exact point? And general relativity gives a precise answer. Quantum mechanics says nothing is so definite. Every physical quantity is subject to uncertainty relations. Position and momentum, energy and time. You cannot know both with perfect precision simultaneously. The more precisely you pin down one, the more the other smears out. At subatomic scales, particles don't have definite positions. They have probability clouds. Fields don't have precise values. They fluctuate quantum mechanically. If matter obeys quantum mechanics and space-time curves in response to matter, then space-time should inherit quantum uncertainty. But general relativity provides no mechanism for this. It demands definite geometry. Something has to give. The problem becomes acute at the Planck scale. Distances around 10 to the minus 35 meters and times around 10 to the minus 44 seconds. At these scales, quantum fluctuations of space-time geometry should dominate. General relativity's smooth, manifold picture should break down completely. But we have no theory describing what replaces it. Here's a historical quirk. Einstein spent his final decades trying to unify gravity with electromagnetism, seeking a single theory encompassing both. He wasn't pursuing quantum gravity. He was skeptical of quantum mechanics' foundations, famously arguing it was incomplete. His unification efforts failed, and most physicists now see them as misguided. The real unification challenge, it turned out, was reconciling gravity with quantum mechanics, rather than unifying gravity with other forces classically. Historians still argue about whether Einstein's resistance to quantum mechanics slowed physics progress or reflected legitimate concerns that others dismissed too quickly. Quantum mechanics works spectacularly well. It underlies all of modern electronics, chemistry, and materials science. But its interpretation remains controversial. Maybe Einstein's discomfort pointed toward genuine problems that a successful quantum gravity theory will need to address. The need for quantum gravity isn't merely theoretical. Black holes present concrete puzzles. When matter collapses into a black hole, what happens to quantum information about the matter's state? General relativity says it falls into the singularity and vanishes. Quantum mechanics says information cannot be destroyed. This black hole information paradox has spawned decades of research and remains contentious. Hawking radiation complicates things further. In 1974, Stephen Hawking showed that black holes should emit thermal radiation due to quantum effects near the event horizon, slowly evaporating over cosmic timescales. This radiation appears to carry no information about what fell into the black hole, suggesting information loss. But information loss violates quantum mechanics' fundamental principles. Something is wrong with our understanding. Either general relativity, quantum mechanics, or both must be modified. The Big Bang presents another quantum gravity puzzle. Run the universe's expansion backward, and you reach a state of extreme density and temperature, conditions where quantum gravity effects should dominate. The very origin of the cosmos lies in a regime where our theories fail. Understanding what happened requires theoretical tools we don't yet possess. Various approaches attempt to bridge the gap. String theory proposes that fundamental objects aren't point particles, but tiny vibrating strings. Different vibration modes correspond to different particles, and gravitons emerge naturally. Loop quantum gravity attempts to quantize spacetime directly, representing it as a network of discrete loops rather than a continuous manifold. Causal dynamical triangulations build spacetime from tiny geometric building blocks. None has achieved consensus acceptance. Each has compelling features and significant problems. Here's the humbling truth. Despite decades of brilliant effort by thousands of physicists, we don't know how spacetime works at the deepest level. General relativity is an approximation that works superbly at large scales but breaks down where quantum effects matter. Quantum field theory is an approximation that works superbly at small scales but doesn't know how to handle dynamical spacetime geometry. The complete theory, if one exists, remains undiscovered. You're lying on spacetime right now, and nobody fully understands what spacetime is. This might seem disturbing, or might seem wonderful, depending on your disposition. The universe still holds secrets. Fundamental questions await answers. The story isn't finished. Perhaps someday a new theory will unify these realms, revealing spacetime's true quantum nature. Perhaps it will require concepts we haven't yet imagined. Perhaps you're already asleep, and this paragraph is drifting through dreams where physics makes perfect sense, or no sense at all, which in dreams amounts to the same thing. The search for quantum gravity has driven theoretical physics for decades, producing ideas that range from elegant to bizarre. String theory, loop quantum gravity, and various other approaches each claim to offer glimpses of how spacetime might work at the deepest level. None has been experimentally confirmed. All remain works in progress. String theory emerged in the 1970s, originally as an attempt to describe the strong nuclear force. It faltered for that purpose, but found new life as a candidate theory of everything, including gravity. The central idea: fundamental objects aren't point-like particles, but tiny one-dimensional strings. Different vibrational patterns of these strings correspond to different particles: electrons, quarks, photons, and crucially, gravitons, the hypothetical particles mediating gravitational interactions. String theory's mathematics proved extraordinarily rich, revealing unexpected connections between physics and abstract mathematics. But it came with puzzling requirements. The equations only worked consistently in 10 spacetime dimensions, not the 4 we observe. Where are the extra 6 dimensions? String theorists proposed they're curled up at scales too small to detect. Compact extra dimensions rolled into tiny shapes at every point in ordinary space. This compactification introduces enormous ambiguity. The extra dimensions could be curled up in vast numbers of possible configurations. Estimates suggest 10 to the 500 or more distinct possibilities. Each configuration yields different low-energy physics. The standard model of particle physics might emerge from one configuration among this landscape of possibilities, but which one, and why that one? Critics argue string theory has lost predictive power, becoming unfalsifiable. Defenders counter that the theory makes general predictions, like the existence of supersymmetric particles, that experiments could eventually test. The Large Hadron Collider hasn't found supersymmetric particles at energies initially predicted, dampening some enthusiasm, though theory allows them to exist at higher energies beyond current reach. Loop quantum gravity takes a different approach, attempting to quantize general relativity directly, rather than embedding gravity in a larger framework. The key insight: just as quantum mechanics quantizes energy levels in atoms, space itself might be quantized. At the smallest scales, space wouldn't be continuous, but made of discrete chunks. In loop quantum gravity, spacetime's geometry is represented by spin networks, graphs whose edges carry quantum numbers describing area and volume. These networks evolve in time through discrete transitions. The smooth spacetime we experience emerges from averaging over vast numbers of these discrete quantum structures, much as smooth water emerges from averaging over countless jiggling molecules. Loop quantum gravity offers concrete predictions about the minimum possible area and volume, roughly Planck-scale quanta. It provides candidate resolutions to singularities. Instead of space-time curvature becoming infinite at black hole centers or the Big Bang, the discrete structure might halt collapse, producing a bounce rather than a singularity. Historians still argue whether loop quantum gravity has made more concrete contact with observation than string theory, or whether its apparent predictions are artifacts of specific assumptions that might not survive deeper analysis. The theory faces its own technical challenges, including difficulty recovering smooth spacetime from discrete quantum structures and incorporating matter consistently. Other approaches abound. Causal set theory proposes that spacetime events are fundamentally discrete, related by causal connections rather than distance. Events form a partially ordered set, and geometry emerges from counting how many events lie between others. Emergent gravity proposals suggest spacetime itself isn't fundamental, but arises from something deeper, perhaps quantum information or entanglement patterns in an underlying quantum system. Here's a quirky recent development. Research into holographic principles and ADS/CFT correspondence suggests that spacetime might be encoded in lower dimensional information on boundaries. A universe with gravity in its interior might be mathematically equivalent to a universe without gravity living on its boundary, like a hologram containing three-dimensional information on a two-dimensional surface. This correspondence has provided new tools for calculations, but raises deep questions about what spacetime really is. The honest assessment: we don't know which approach, if any, points toward truth. Perhaps string theory will eventually achieve experimental confirmation. Perhaps loop quantum gravity will explain some observed phenomenon. Perhaps all current approaches are wrong, and the correct theory awaits discovery by minds not yet born. Science tolerates this uncertainty uncomfortably but productively. The tension drives research, funds experiments, inspires new ideas. Future gravitational wave detectors might probe regimes where quantum gravity effects emerge. Future particle accelerators might reveal hints of extra dimensions or supersymmetry. Or future astronomers might observe phenomena that current theories cannot explain, forcing revolution. You drift now in a universe whose deepest nature remains hidden. The fabric you rest upon, space-time, curved and mysterious, hasn't revealed its ultimate composition. The hunt continues. Physicists strain at the boundaries of knowledge, pushing equations into unexplored territory, hoping to glimpse what lies beneath. What if spacetime isn't fundamental? What if the four-dimensional fabric we've been discussing all night is actually emergent, arising from something deeper, simpler, more abstract? This possibility, radical as it sounds, has gained traction among physicists seeking quantum gravity. The analogy often invoked is thermodynamics. Temperature and pressure feel fundamental when you experience a cold wind or a compressed gas. But they're not fundamental. They emerge from the statistical behavior of countless atoms. Temperature is a shorthand for average molecular kinetic energy. Pressure summarizes how momentum transfers during molecular collisions. The macroscopic phenomena are real and important, but they arise from a microscopic level where temperature and pressure don't exist as fundamental concepts. Perhaps spacetime is similarly emergent. At everyday scales, it appears smooth, continuous, described perfectly by general relativity. At extreme scales, Planck lengths, Planck times, something else might underlie it. Spacetime's curvature, distances and durations might be macroscopic averages over some quantum substructure. What might that substructure be? Proposals vary wildly. One influential idea connects spacetime to quantum entanglement. Entanglement is the quantum mechanical phenomenon where particles become correlated in ways that can't be explained by shared information. Measuring one instantly affects what you'll find measuring the other, regardless of distance. Einstein famously called it spooky action at a distance, and used it to argue quantum mechanics was incomplete. Recent research suggests entanglement might do more than connect particles. It might create spacetime itself. In certain holographic models, the geometry of a spacetime region correlates with the entanglement structure of fields on its boundary. More entanglement between boundary regions corresponds to those regions being closer together in the bulk spacetime. Spacetime geometry might literally be woven from quantum correlations. This is called the ER equals EPR conjecture, named for two papers Einstein co-authored, one on wormholes, Einstein-Rosen bridges, or ER, and one on entanglement, Einstein-Podolsky-Rosen paradox, or EPR. The conjecture proposes they're secretly the same phenomenon. Every entangled pair is connected by a tiny wormhole. Spacetime connectivity reflects entanglement structure. If this sounds speculative, it is, but it's productive speculation, generating new mathematical tools and potential experimental tests, and it addresses a deep puzzle. Why should spacetime have the geometry it has? If spacetime emerges from entanglement, then the laws governing quantum information shape the laws governing gravity. The connection is not coincidental, but fundamental. Here's another approach. Spacetime might emerge from something resembling a quantum computer. The universe might be a vast computational process, with physical reality as its output. This isn't mystical hand-waving. It's serious theoretical work exploring how informational primitives could generate spacetime geometry. If the universe computes, then its computational architecture determines physical structure. Historians still argue whether these ideas represent genuine progress or elaborate mathematical games divorced from physical reality. The distinction is sometimes hard to draw. Many successful theories in physics began as mathematical games. Dirac's equation for the electron seemed like formalism before experimental confirmation, and gauge theories were abstract constructions before experiments vindicated them. Mathematical elegance sometimes anticipates physical truth. What we can say confidently, spacetime as we understand it probably isn't the final word. General relativity breaks down at singularities and can't accommodate quantum effects. Whatever replaces it will likely reveal spacetime as approximate, emergent, a macroscopic appearance arising from something more fundamental. This possibility is philosophically dizzying. Space and time feel like the background within which everything else occurs. Saying they emerge from something deeper requires thinking about what before and where even mean when space and time don't yet exist. The language of causation and location becomes treacherous. Perhaps this is why human intuition fails at the deepest levels. We evolved to navigate spatial environments and temporal sequences. Our brains are optimized for space-time reasoning. Asking us to think about what lies beneath space-time is like asking fish to contemplate land. We lack the cognitive equipment. We build mathematics to extend beyond intuition, and mathematics suggests space-time might be surface rather than substrate. Tonight, as you dissolve towards sleep, consider that you're dissolving into something that might not be ultimate reality. The space-time fabric surrounding you, the distances between your heartbeats, the intervals between your breaths, might be emergent phenomena, shadows cast by deeper quantum structure. The shadow feels real because you're made of it. But what casts the shadow? Science doesn't know. Science is looking. And the search itself reveals something remarkable about human minds. We can question even the ground we stand on, even the time we live in, even the categories that structure our experience. We can grope toward truths our intuitions can't grasp. You've journeyed tonight through ideas that transformed humanity's understanding of reality. From Newton's absolute time, ticking uniformly everywhere, through Einstein's revolutionary fusion of space and time, to gravitational waves rippling through the cosmos and black holes bending space-time into strange geometries. You've encountered the block universe, where past and future exist eternally, and the quantum gravity frontier, where space-time itself might dissolve into something deeper. And here's the remarkable truth. Despite all this, we still don't fully understand space-time. We use it. We navigate by it. Our technologies depend on it, but comprehend it. Truly grasp what it is, where it comes from, why it has the structure it has. That remains beyond us. This might seem like failure, but it's something more interesting. It's honest engagement with reality's genuine complexity. The universe doesn't owe us simple answers. It offers hints, patterns, mathematical regularities. It rewards careful observation and rigorous reasoning. But it doesn't surrender all its secrets on demand. Einstein spent the second half of his life searching for a unified theory, a single framework explaining all forces and all phenomena. He died without finding it. Decades of subsequent work by thousands of brilliant physicists have advanced our understanding enormously, but haven't achieved the final synthesis. Perhaps that synthesis exists and awaits discovery. Perhaps reality is irreducibly plural, resisting unification. Perhaps the question itself is wrong in ways we can't yet articulate. Here's a historical perspective worth savouring. Every previous generation of physicists thought they were close to final understanding. 19th century physicists saw only two small clouds on the horizon of an otherwise complete picture. Those clouds unleashed relativity and quantum mechanics, overturning everything. Perhaps our current puzzles, quantum gravity, dark matter, dark energy, the measurement problem, are similarly small clouds concealing revolutions. Or perhaps not. Perhaps we're closer to fundamental truth than any previous generation. Perhaps the standard model of particle physics and general relativity, with minor modifications, capture reality's deep structure, and the remaining puzzles are technical rather than revolutionary. We don't know. We can't know yet. Science proceeds by proposing theories, testing predictions, revising understanding. The process has no guaranteed endpoint. What we can celebrate is how far we've come. A century ago, nobody knew that time dilates with motion, that gravity curves space-time, that the universe expands from a hot, dense state. These discoveries emerge from human minds applying reason to evidence, building mathematical structures that captured aspects of reality beyond ordinary perception. The enterprise is astonishing. You're a beneficiary of that enterprise. The knowledge we've discussed tonight, knowledge about space-time's flexibility, about time's locality, about the cosmic geometry you inhabit, was hard-won over generations. It represents humanity at its best, curious, persistent, willing to question sacred assumptions, committed to evidence over dogma. And here's perhaps the strangest comfort. You don't need to understand space-time to rest within it. Fish don't understand hydrodynamics. Birds don't understand aerodynamics. You don't need to grasp the mathematics of curved manifolds to experience the universe they describe. You're living space-time, tracing your world line, accumulating proper time along your trajectory through the cosmos. Understanding is optional, existing is mandatory, so let go of the equations, let go of the puzzles, let go of the unresolved questions that keep physicists awake at night. Tonight, you're not a physicist. You're a pattern in space-time, an eddy in the cosmic flow, a brief but beautiful arrangement of matter and energy following geodesics through a geometry that shaped itself over billions of years to hold this moment. You, resting, breathing, letting consciousness soften towards sleep. Let your thoughts dissolve now like morning mist. The numbers and theories, the paradoxes and predictions, they drift away, leaving only the gentle sensation of being held. Space-time holds you. It always has. Since before you were born, through every moment of your life, it has curved around you, carried you, provided the stage and the tempo of your existence. You don't need to think about it. You can simply rest in it. Feel your body heavy against the bed. Feel time passing slowly, gently, at exactly the rate it passes for you. Here, now, in this small region of curved space-time you call home. The universe is vast and strange. Black holes swallow light. Gravitational waves ripple from ancient collisions. The future might already exist, waiting along your world line. And none of this diminishes the warmth of your pillow, the softness of your breath, the quiet closing of your eyes. Einstein himself found peace in contemplating the eternal structure beneath passing moments. You too can rest in that structure, not understanding it, just resting in it. Tomorrow the sun will rise because Earth rotates through the space-time geometry established by gravity and motion. But tonight, you don't need to trace those mechanics. You only need to let them carry you effortlessly into sleep. The cosmos holds its mysteries. Let it hold you too. Breathe slowly, breathe softly. Your world line continues, but your waking mind can pause. Let sleep arrive like a traveller returning home. You've journeyed far tonight. Now rest. Sweet dreams, traveller through space-time.